Hi, I'm hoping everybody had a wonderful 4th of July holiday, and today is July 5th, and we're talking about section 2.5, okay? Getting rid of the ink. So we're going to be talking about linear independence, which is defined as the opposite of linear dependence, but we'll get into that. Um, Now would be a good time to open up Matlab. I'm going to show you a couple new tricks that will be cool to know. And remember, you can take notes in Matlab as long as you remember to save your notebook when you are done. Okay, so I'm assuming that you're done and that you've opened up Matlab. Okay, so what is linear dependence? Okay, so linear dependence and linear independence refers to a set of vectors. Okay, so we've just got some number of vectors, v sub 1, v sub 2, up through v sub k, and they're all the same dimension. Okay, so when we say a set of vectors, v sub 1, v sub 2, up through vector v sub k, we mean that they're all the same length. Okay, so if we have this set of vectors, they're called linearly dependent if there exists a non-trivial linear combination of the vectors that is equal to the zero vector. Okay, now what's this non-trivial bit? Okay, well, we'll get to that. All right. And so the definition of linear independence is a set of vectors that is not linearly dependent. Okay, so instead of defining linear independence, we're defining what it means to be linearly dependent. One of these non-trivial linear combinations of the set of vectors that's equal to the zero vector. That's linearly dependent, right? And then independence is not dependent. Okay, well, let's start to make this a little more concrete. So linear dependence, what does it say? Okay, look, we're just talking about all possible linear combinations of the vector x with the set of vectors. So x sub 1 is component 1 of the vector x, right, multiplied by the vector v sub 1. And sorry, there's a stray 1 in here, just ignore that. Right, and I'm sorry, this should be x sub 2 and v sub 2. I'm sorry, I didn't get the copy pasting done correctly. Um, okay, so we're just taking the second component of x times vector v sub 2, and we're taking the kth component of x times the vector v sub k. And the question is, does it equal the zero vector? And again, sorry about that. Mistyped um, equation there. But yeah, we're just saying if we take the product of these vector components of x as scalar multiples of the vectors, the set of vectors, and add them up, is it possible to create such a vector x so that the linear combination equals the zero vector? If there is, they're linearly dependent. As long as this non-trivial bit, what in the world is this non-trivial bit talking about? Well, let's get rid of the ink and jump to the next slide. And jump to the next slide. There we go. Okay, so now I got the linear set of vectors v sub 1, v sub 2, up through v sub k. It's typed correctly. And so what we're going to do is we're going to create a matrix A from these vectors. What are we going to do? Well, each vector becomes a column of A. And notice that what is important that I said on the previous slide that they're all the same length, the same dimension, right? Because I can't make a matrix if one of these vectors has length 3 and the rest of them have length 6. You know, that's not a matrix. And there's no rules about filling in elements in one vector if it's shorter than another. All right. So again, set of vectors, when we say this, right, we are saying that they're all the same length. Sorry, I probably should just say it rather than try to type it because as you've seen before, I do not type very quickly or very legibly. Oh, this is turning out pretty well. Okay, so we have a set of vectors, meaning that they're all the vectors are the same length, okay? So now we're gonna just take each vector, v sub 1 up through v sub k, and make it a column of a matrix. And let's call it matrix A. You can call it whatever you'd like, but we create this matrix whose columns are the vectors v sub 1, v sub 2, up through v sub k. And so what we're looking for is a vector x so that when I multiply it by A, it equals the zero vector. And if you think about it, this is exactly what it means if we do those dot products, right? Because what are we doing? We're taking the top row of A times the vector x, which does what? It gets the first component of x times the first column of A. And the second component of x is multiplied by the second component of A. Every single time we do this for row 1, row 2, row 3, row 4, however many rows there are in A, excuse me. Yes, we do this for row 1, row 2, row 3, however many rows there are, right? So the first component of x is always multiplied by a first column entry of A. So we end up creating a linear combination of the columns of A. That's what this is saying. Find me a linear combination of the columns of A such that the linear combination is equal to 0. All right, that seems somewhat straightforward. Okay. The trivial is solution. Okay, so it turns out that if I just say, hey, let's make everything in here 0. If every single component is 0, then of course this equals 0, right? The linear combination of 0 times the first column plus 0 times the second column plus 0 times every other column. I just have a bunch of zeros, which is then when I multiply it by A, no matter what A is, it doesn't matter what's in A. If I multiply it by the 0 vector, I get the 0 vector. So that's called the trivial solution, and it always exists. So we're looking for a non-trivial solution. We're looking for something, right? Some vector x where at least one component of x is not 0. Now it turns out there'll have to be 2, but again, we're looking for a set of vectors x such that, or excuse me, we're looking for a vector x such that a times the vector x is in fact equal to 0, but x has to have some components that are non-zero. Okay, so why are we doing this? Okay, well, it turns out that here's the big deal. We can determine linear dependence, right? Given the matrix A. And again, remember that we're thinking of the set of vectors as the columns of A. Okay, so even if I don't start with a set of vectors, I can think of the columns of A as a set of vectors. Okay, and then I create the augmented matrix. You recall from earlier, we're calling this the homogeneous set of equations. Okay, so I can take a look at the homogeneous set of equations. After I've augmented that matrix A with a 0 vector, I row reduce to RREF. And then the question is, does a non-trivial solution exist? All right, so we take a look at X, like this solution vector X, and we just check, kind of as a question mark above the equal sign, is X equal to the 0 vector? Okay, and if the answer to that question is yes, right, if a non-trivial solution exists, then they're linearly dependent. If no non-trivial solution exists, they're linearly independent. Okay, so that's the key takeaway. And as I said before, when we were first looking at this slide, remember we can think of the columns of matrix A treated as a set of vectors, or we can think of a set of vectors and create matrix A by taking each of the set of vectors, each vector in the set, and making it a column of A. Okay, so either way, we can check to see, and that's what we mean if we talk about a matrix and linear independence or linear dependence, right? We're talking about that matrix with its columns considered as a set of vectors. Okay, so let's jump over into MATLAB and see where we get with some examples. Okay, so here's MATLAB, and I have actually copied um, the example from section 2.5. So I'm looking at the set of online notes, right? And the very first thing, oh, I'm sorry, there should be an N in here, an ND, wait, no, I have it right. Independent. Oh, an N in here. Okay, I knew there was, it felt like it was missing an N between the E and the D there. Um, but what I did was I created this example in MATLAB to go over. I'm going to show you those steps. So let's jump back over to this other tab where I have MATLAB open. And so we're asking the question, is this set of vectors linearly independent? And this is what was on the slide, right? It gives me the steps. Create this augmented matrix of A with augmented with a zero vector, and then row reduce that. By the way, this, I thought I had fixed it. But this should be RREF, okay? So, um, and ask ourselves, does a non-trivial solution exist? If yes, we have linear dependence, and if no, then we have linear independence, okay? So that's how it goes. And so again, you'll notice that these vectors x sub 1, x sub 2, x sub 3, they do in fact match the vectors over here. And here we created a matrix X. Over here, I created a matrix A. Okay, and let me remind you that the semicolon separates the rows, right? So then with a vector, I just create each component separated by a semicolon, and I get this column vector that I'm looking for. And when I put the semicolon after this, it suppresses the output. So it's not going to, these first three commands are not going to create any output. Just, I'll see if I get matrix A right. Let's hit Control Enter, and there you go. And notice that the -1, -2, -2, the first vector is correct, -2, 1, 1, the second vector is correct, 0, 4, 3, this third vector is correct. So in fact, A is right. A is the set of vectors x sub 1, x sub 2, x sub 3. Its columns are that set of vectors. Okay, so now we're going to augment this, and let me just show you this zeros 3, 1. Check out what this does. This just creates a zero vector. It actually will create a zero matrix, but I put 3 rows, but only 1 column. So if I specify just 1 column, it's creating a zero vector. If I specify like 3 by 3, it'll create, well, let's try it, right? So it'll create whatever size matrix I ask it to, and just fill it with zeros. Why am I doing that? Well, because what I want to do is I want to augment the matrix A with the appropriate zero vector, okay? So there are other ways to do this, but I wanted to show you this neat little trick, right? Zeros 3, 1 just gives me the correct dimension of the zero vector, and you'll see, aha, now I have exactly what I was looking for. I have this augmented matrix of capital A with the zero vector, and it's called little a. All right, and now we can row reduce it. Now, I could, if I wanted to, do the row reducing steps. I'm not going to. I am going to do the quick RREF of little a. Why? Because I don't need, at the moment, to do another example. I've done several examples throughout this semester of how to do the row reducing, and you should know how to do that row reducing. But we can use RREF here. Why? Because we're just asking ourselves, is there a non-trivial solution to this? Okay. Well, what's the solution? We see that the first equation tells us that the value x sub 1 is equal to 0. And the second row tells us what? That x sub 2 is equal to 0. And the third row tells us that x sub 3 is equal to 0. Sorry, that looks more like a 6 up there. That's supposed to be a 0. Okay. All right. So what does that mean? Does that mean we have linear independence or linear dependence? Well, this is the trivial vector, right? Basically what we're saying is, hey, the vector x is in fact equal to the 0 vector. But that's trivial vector. So when we row reduce, we find that the solution is the trivial vector, and there are no non-trivial solutions. There are no non-trivial solutions, so in the first example, these vectors x sub 1, x sub 2, x sub 3 are in fact linearly dependent, right? If the only solution that we can find is the trivial solution, if the only linear combination we can find is the trivial one, then they're dependent. All right, so let's get rid of the ink and try another example. I've done the exact same thing, even including using the zeros function in Matlab to create the vectors y1, y2, y3. Okay, and so you can see that we do in fact have the correct augmented matrix. All right, and so I'm going to do the same thing, RREF of B. Now this is interesting. Okay. Why is this interesting? Why am I saying this is interesting? Well, because first of all, the third row says 0 equals 0. That's not a big thing for us. But look at the second row. The second row tells us what? That x sub 2 plus 1/3 x sub 3 equals 0. Okay, so x sub 2 equals minus 1/3 x sub 3, right? I can move the 1/3 x sub 3, the free variable, over onto the right-hand side, so I can solve for the basic variable in terms of the free variable. And it turns out that I have something that works. And also notice that the top row tells me that x sub 1 equals 1/3. Sorry, this is ugly. 1/3 x sub 2. And what am I saying? Hey, we've found a non-trivial solution. These are not going to be equal to the 0 vector. All right, since they're not equal to the 0 vector, I've found a non-trivial solution. Okay, so when there's a non-trivial linear combination of the rows of B, such that the linear combination is in fact equal to 0. Non-trivial linear combination that's not equal to the 0 vector. Excuse me, okay, the vector x, right? Right, the vector x is not equal to the 0 vector. Of course, the linear combination is equal to the 0 vector, but x isn't equal to the 0 vector. We don't have the trivial solution. So here we have independence, right? So the first one was dependent. The second one is independent. And again, it all comes down to the form of the solutions, right? For the augmented matrix B, we did in fact find a linear combination. Now it's going to have a 0 component, right? X sub 3 is going to be equal to 0. That's interesting. I'm going to think about that for a moment. No, we don't have a 1 here. So we don't know that x sub 3 is equal to 0. X sub 3 can be anything because it's a free variable. I'm sorry. but we have a non-trivial solution here, and in the one above, we had only the trivial solution. So that's how we tell the difference between independent and dependent. Okay, so your online notes take a slightly different look. It still works. The theory is the same, but the online notes ask how many pivots are there? Because the pivots will correspond to the actual vectors that are linearly independent. Okay, so when we row reduce matrix A and we get 3 pivots, I know that there are 3 linearly independent vectors. Well, that's all of them, so the entire set of vectors is linearly independent. All right, and then looking at the next example, when we row reduced it, we got 2 pivots. Okay, well, that's fine, but we still have 2 pivots. We have some things that are non-zero. Therefore, there must be a non-trivial solution to the homogeneous set of equations. So that's another way to look at it. You can actually think about solving that set of vectors row reduced to RREF, or you can think about it just the pivots will correspond to all the vectors in the set that are linearly independent. And if all of the vectors correspond to a pivot, then they're all linearly independent. If not all of them correspond to a pivot, then they're not all linearly independent, so we have linear dependence, okay? Okay, fun stuff. So linear dependence relation. So let me just, before I go through this, let me just say that sometimes people will say, well, hey, if this set of vectors is linearly dependent, what is that linear dependence relation, right? I don't know. How do we find that? So that's what this part is about. We're going to say, all right, suppose we think that this set of vectors is linearly dependent. Can you find the linear combination that actually does the trick, right? We're still trying to solve we're trying to find the solution vector x, right? A times the solution vector x equals the 0 vector, right? That's what it means to be linearly dependent, but hey, what is this solution vector? Maybe we can use it to find out what this linear dependence relation is. And let's try it. Let's get rid of the ink and let's try it. So instead of augmenting it with the 0 matrix, we just treat the matrix A as an augmented matrix by what? By making its last vector the solution vector, and then the coefficient matrix is just a 3 by 2 matrix, okay? Whatever's on the left side of the augmentation bar there, right? And we row reduce and get the exact same thing we got above, okay? And we found this solution vector, and they're doing vector v rather than vector x as a solution vector, which is fine. But again, how do I get this 1/3, 1/3? Well, it's right here, right? X sub 1 equals negative a third, and x sub 2 equals positive a third, which is exactly what we have. And so the third vector is a linear combination of the first two. And the vector v is the one that makes it equal. Okay, and then I go through some math in the that makes sense, and you can check it out. Again, just creating the 3 vectors. These are creating empty vectors. Sorry. No, I'm sorry. The matrix is called Y, so this is taking the first column of Y, the second column of Y, the third column of Y, and it spits out Y1, Y2, Y3, just like we need it to. And then I'm doing minus Y1 divided by 3 plus Y2 divided by 3. Okay, that is the linear combination if you think about it. And notice what we get. We get 1, negative 1, 0. And is that equal to y sub 3? So when I use the double equal signs, It's not an assignment, it's a question mark, right? Is negative y sub 1 divided by 3 plus y sub 2 divided by 3 equal to y sub 3, question mark? Well, we get this logical array because it actually checks every single component and throws up a 1 if the answer is yes and a 0 if the answer is no. Since we have ones on every value, it is in fact equal. Therefore, we know that this is true. This is the linear dependence relation. Why? Because the third vector, the third column of A, we found a vector V that, right, that works, right? So that A times, well, I'm sorry, it's not really A. It's the first two columns of A, my bad. But, we found this vector V, right? This component and this component are the components of the vector V that actually creates the linear dependence. Okay, so not that bad. Let's get rid of the ink and just do this last thing, spans and linear dependence. This is mostly just a definition. Okay, so we say that a vector B is in the span of a set of vectors if there's a linear combination of the vectors that equals B. Interesting. So if B is a linear combination of the set of vectors, then it's in the span. If we can't find a solution, right, a linear combination, so that the vector B is equal to that linear combination, it means it's not in the set. It's not in the span of the set, sorry. So notice it's kind of the same thing that we've been doing, right? We're treating this vector B as what we're looking for, and then we're trying to find some linear combination of the set of vectors so that the linear combination equals B. If we can find that linear combination, we know that the vector is in the span, right? And if you think about it, we're just finding a linear dependence relation for B. So if we can find a linear dependence relation for B based on the vectors, the set of vectors, right? If we can find a linear dependence relation, then B is in the span. If we can't find a linear dependence relation, then it's not in the span. And why do we care if it's in the span? Well, stay tuned. The very next video will explain that.